right? Here it is, right? If you make u1 to be 2u1, u2 to be 2u2, and un to be 2un, everything here is exactly multiplied by a factor of 2. It doesn't have to be a factor of 2. It can be a factor of anything, right? It can be a factor of a, and the output is multiplied by a factor of a. So that's the first criterion of linearness. The second criterion is if you have one set of values, let's call u, another set of values, let's call v. It has to satisfy the principle of linear superposition, which means if the input is the sum of these two sets of values, the output is going to be exactly the sum of the two outputs if you put the two sets of values individually into this operator, into this transformation, right? So basically, it doesn't matter whether you add it up, then do the transformation, or you do the transformation, then add it up. If that's true, if these two criterions are true, one is it doesn't matter if you multiply something, then do the transformation, or you do the transformation, then multiply that thing. The second is it doesn't matter if you add them, then transform, or transform, then add. Then this is linear, right? So this operator here, you can check that with all of these approximations, and you are going to see that all of these approximate derivative operators are linear. An operation being linear actually is pretty significant because you can write it in matrix form. And being able to write it in matrix form makes it very easy to use computers. There was a famous pretty early computer science that says that computers are good at doing two things. The first thing is logic, right? If-else stuff. And the second is linear algebra, essentially. If you can represent things in matrix form, you have a much easier time using computers to solve the problems. All right, here, let's try to represent this particular linear operator into matrix form. All right, and if we can do that, if we can represent this into a matrix form, we multiply the matrix with A and move it to the right-hand side, we get an ODE in a matrix form, right? And then we can analyze its eigenvalues. So being able to represent these, right, in matrix form is going to be very useful. So let's try. I'm going to write down my output, u2 minus u1 divided by delta x, u3 minus u2 divided by delta x, etc. How can I write it as a matrix times the vector of u1, u2, etc. to un? Okay, again, let's look at row by row. What does the first row look like? Yeah, next to 1 over delta x, how can I tell? Because this is the term that's supposed to be multiplied with u1 and contribute to the first output, right? And the coefficient on u1 here is negative 1 over delta x. Good job. The second column is 1 over delta x, right? That is supposed to be multiplied with u2 and add again to the first output, okay? And that is 1 over delta x. How about the rest of the row? Zeros, right? And usually when in a matrix, if I don't write anything, that means these terms are zeros. All right? Okay, so that completes our first row. How about the second row? It's the same except it's shifted over, exactly. So in this case, u1 actually doesn't appear in the second output, which means u1 is multiplied by 0, right? And then u2 here fulfills the same row as u1 in the first output. So u2 would be multiplied by the same coefficient as u1 in the first row, right? Which means minus 1 over delta x. And u3 actually fulfills the same row as u2 in the first row. So we have plus 1 over delta x. and the rest is all 0. Now you can see that the third row is also pretty much the same, except it is shifted by one more item. So I have 2 zeros, I have minus 1 over delta x, I have 1 over delta x, and a bunch of zeros. Okay, so and this continues to the very end, and there is a little bit special at the last row. What is it? So for this matrix, first of all, this matrix is a square matrix. What that means is that the number of columns is the same as the number of rows, right? A square. Okay, and if it's a square, then this diagonal of minus 1 over delta x has to continue all the way to here, right? So the very last item is actually the same as the very first item, minus 1 over delta x. So where does the plus 1 over delta x go? Goes to the first column, yes, because of the periodic boundary condition. Remember, the last row is u1 minus un divided by delta x. So u1, which has the coefficient of plus 1 over delta x, goes to here, right? So this is actually special to periodic boundary conditions. If you have something else, the last row doesn't really wrap over, right? You have to, the first row and the last row is actually could be sensitive to what boundary conditions you are specifying. But if I have periodic boundary condition, then the rows just shift over and it rolls over. Okay, so now this is my matrix. Okay, first of all, let's actually take a brief look at what eigenvalue this matrix have. Okay, I'm going to make a matrix, and I will just say an arbitrary n. Let's just start small, actually n equal to 10. Okay, my delta x is equal to 1 over n, and my matrix. So let me actually tell you a little bit of tricks to constructing such matrices. First of all, I want to fill my diagonal. And if I have a diagonal with the same numbers, it's pretty easy to fill. So if I type in I of n, I have the identity matrix, right? And if I have I of n times minus 1 over delta x, I have minus 1 over delta x filled in the diagonal, right? So that actually is exactly what I want on the diagonal. But then I have a little bit more on the item that is on the right hand side of the diagonal. And in linear algebra, we usually call it the upper diagonal, right? So it's on the right or on the upside of the diagonal.